to me, the missing piece is the fact that our diets have gone to just eating the muscle meat. Because if we were to eat the whole animal
Right.
and get things like collagen, gelatin, make bone broth, then we're getting the glycine on a regular basis and complementing naturally the methionine.
Right. The way I put it is to say that whatever culture you come from whatever part of the world, your grandma or your great-grandma didn't throw the bones into the trash. She threw the bones into the soup because, everybody needed that. We now are in an age and a particular era of civilization where we have an overabundance of food. And so, we take the food that we like to eat, that's easier to eat. We cut the bones, cut the muscle off the bones, and that's exactly right. We eat the muscle, which is very methionine rich, and we throw away the bones. We throw them into the trash instead of the soup. And we get more than one bad effect from that. We get kind of a double whammy for the simple reason that the glycine, which we are not eating, is actually what is needed to clear away the excess methionine. So when we eat more muscle meat than we need, for every single molecule of methionine that our liver needs to get rid of, it uses up 2 molecules of glycine. So we get hit. First of all, we're not eating enough glycine, and then we're eating too much methionine. And so what does that do? That, that ends up stripping the glycine that is, that's otherwise needed for everything else that glycine does. And the key finding about glycine, and I think the one that I have focused on, and the one that drove me to the realization that we really need supplementation, is that glycine, you can say, well, it's the most abundant or the second most abundant amino acid in the body. Your body makes plenty of it. You make several grams a day, but you need to have another 10. The usual diet gives you about 2 or 3. But nobody dies from glycine deficiency. We know about rickets from vitamin D deficiency, but nobody's ever had a glycine deficiency disease. We seem to have enough glycine to make all the protein we need, even collagen. That slows with aging, but it's probably more of an aging phenomenon than a glycine deficiency problem. Well, that's because glycine not only has a number of functions biochemically, including being one of the building blocks of protein, that it's also a donor of 1 and 2 carbon units to make purines and pyrimidines, the building blocks of DNA, the nucleotides, and so on, and also neurotransmitters and other things. But it has this function in inflammation, has nothing to do really with biochemistry, except that the biochemistry uses it up. So biochemically, most of the glycine in a healthy body serves as a reservoir that can be used for all the biochemical needs. But what it does in inflammation is not biochemistry. It's actually cellular physiology, because what the glycine does is it binds to those glycine receptors, which are actually gated channels, right? There are pipes that run through the cell membrane to connect the inside of the cell and the outside of the cell. There are different kinds of gateways which allow different substances in and out. And one of the key ones is called a glycine-gated chloride channel. And it allows chloride ions to come in. See, there's a balance. The chemical balance inside and outside the cell, the ionic balance, means that generally speaking, the potassium is very high inside the cell, sodium very low. Sodium very high outside the cell, very low inside. Chloride high outside the cell, very low inside. Well, chloride has a negative charge to it. Chloride ions, sodium ions, and potassium ions have a positive charge to it. The resting potential of the cell between inside and outside is actually where there is a negative charge inside, net negative inside, and positive outside, kind of like the switch on a wall. If you have a switch on a wall, you have, and the light switch is off. That means the 2 poles of the switch are at a potential of 120 volts, right? That's, 110 volts, 120 volts, usual voltage. When you turn on the switch and you close the switch, now the potential between the two poles is 0. Now the switch is depolarized, the light goes on. So now if you're a macrophage or a neutrophil minding your business and you see the chemical signature of an E. coli or something else that does not belong there inside the internal part of the body, the internal tissues of the body, it will induce a depolarization. And it will allow like calcium to come in, and once the depolarization happens, you get an activation to this like M1 state. Well, in the course of an M2 macrophage doing its business, it's going around phagocytizing things. It's acting like an amoeba, going around eating up dead cells, cell debris. In the meantime, of course, with all this cytoplasm moving around in bulk and so forth, you have a natural leakage of ions. So naturally, some potassium's going to leak out, some sodium's going to leak in, and there are constantly pumps operating that actually use up energy, ATP, like a bilge pump in a boat. Boat is on the sea. There's always a pump going to pump out water because some water always splashes in. Same thing is true with a macrophage on the high seas of the human bloodstream. Some sodium is going to splash in. Some potassium is going to splash out. And what that's going to do is it's going to lower that voltage from 70 millivolts, not 120 volts, 0.07 volts or thereabouts, that's the resting potential, is going to deteriorate. And if that deterioration is not made up by pumping the right ions in or out, what's a cell to do? Well, the chloride channels are selective for chloride. They allow chloride ions, which are negatively charged, to come in. So when those channels are open, the chloride ions come in, hyperpolarizing the cell because it's ordinarily negative on the inside, positive on the outside. So it raises that potential and keeps that cell from depolarizing. And the more glycine you have, the wider open the glycine-gated chloride channel. So the glycine molecule is not participating in any reactions biochemically. It's a hand on the valve that's working the valves that allow chloride ions to come into the cell, or not enough. And that's really the balance of what goes on. And when you raise it enough, when there's enough glycine around, you don't get inflammation triggered inappropriately or excessively. And that's basically the whole story. It comes down to being as simple as that, in my view.
If you enjoyed that clip, you're going to want to head over here and catch the full episode. I'll see you over there.
Contrary to what it says in any source you look at, that inflammation is the immune system's first response to infection or injury, it is really only a first response to infection. Inflammation does the body